Welcome to the Emerging Technologies panel. We have Dirk Colby from Michigan State University. Maria, I'm going to screw up your last name. Maria Bushkova of the University of Notre Dame. Anita Schwartz from the University of Delaware. John Doty, oh, I screwed up your name. Doty from Tufts University, and David Chin from Drexel. So we're just going to go straight into presentations. They're going to be 5 to 10 minute presentations, and then we'll take questions after.
Hello, everyone. Let's see. So I get to talk to you all about field programmable gate arrays, or FPGAs. Why am I talking about this? Well, a long time ago in a previous life, I used to teach classes on FPGAs and embedded systems. And a couple years ago, I did a sabbatical with a company that used FPGAs to build smart cameras. But more specifically, our department at Michigan State University has just bought 2 nodes with the Intel version of FPGAs on it. And we started a task force. And the task force is a bunch of researchers across campus who are interested in porting codes to these technologies and trying to learn how hard it's going to be and all the nuances of it. And this summer I've been working with a grad student who has been doing an independent study just to do the basic stuff, the hello world type stuff, get it up and running, figuring out how things work. And this fall, we're teaching a course, with our grad students, and we're going to attempt to port all of the 7 dwarf algorithms, which are a set of algorithms used in, pointed out in computation. I forget, it was a Berkeley paper at one point. They're the 7 common algorithms used in computational sciences. We're going to implement those and do a benchmark comparison as a class, and we're going to see how that works. So that's why I am giving this talk, although I am not an expert at FPGAs, though I've got probably 5 minutes more experience than some of you, so that's why I get to do the talk. So let me give you a quick overview of how they work. You have your traditional GPUs and CPUs, which are instruction-driven processors, right? You give it a set of commands. We all know how we program them, and they do the math that we tell it to do. So there's a program coming in on one side, data coming in one side, and out comes your output. Okay? Both GPUs and CPUs work with this. But the speed you get out of these technologies, since they're general purpose, is limited. And actually print it onto hardware. Like, write the gates that do exactly what you want to do without having to have all the overhead of your bus and all this other, your command pipelines and all this other stuff that's in a normal chip. You can go much faster, okay? So if you can take your program and put it on a chip, like in hardware, you can go significantly faster. There's this class of chips called ASICs with application-specific integrated circuits. These are exactly what happens. So Google has this thing called TensorFlow, and a lot of people use it for a lot of things, and they keep doing the same calculations over and over and over again. So they actually made a chip dedicated to doing TensorFlow called the Tensor Processing Unit. And it's super fast compared to running on a GPU or CPU. Similarly, there's a molecular dynamics chip called doing the same thing, doing molecular dynamics code. Although, just to be clear, they stopped this project because the next generation is a GPU beat them. The problem with ASICs, of course, is you have to print a chip and they can only do one thing. They can do it super fast, but also it's usually super expensive. The third example of chip is Bitcoin mining. So for the longest time, you had GPUs doing Bitcoin mining, but they're doing the same commands over and over again. And so a bunch of companies have now printed chips that just do GPU mining, and they can print them at quantity, so they're much cheaper than the GPUs. So those are examples of ASICs. Okay, so you got the super speed, but you're locked in versus the flexibility of a GPU, CPU. And then an FPGA kind of falls in the middle. It's reconfigurable hardware. So you have these arrays of gates, and you can tell the gates how they're wired together. And you can turn an FPGA into a chip that you want. So in theory, you can take an FPGA and turn it into a CPU. Actually, that's done all the time. You can take an FPGA and turn it into a GPU. You can take an FPGA and turn it into whatever processor you want. Okay, so that's the idea behind an FPGA. They're very flexible. It's a programmable hardware. So very cool technology. For some applications, it may be significantly faster than GPUs, right? Because of the architecture, get speeds out of FPGAs for specific calculations much faster than GPUs, CPUs, and everything. So they're very promising technology. This is why Intel announced at Supercomputing 2000s that they're putting their eggs into the FPGA basket for large-scale computing. However, this is an important key. FPGAs are really hard. Now, not only are you writing a program, you're writing the hardware. And when you're optimizing your code, you have an exponentially harder problem to optimize, right? You have to rewire the chip and rewrite your code to work with the rewired chip. It is super hard to do. The potential gains are huge, but it's also a lot of extra work. Configuring the hardware is tricky. I think I got the acronym wrong. I always get what's the VHDL. That's how you actually draw a circuit in a computer and they can print it on the FPGA. But Intel has been investing in an OpenCL library that is really exciting. So you can write your code in OpenCL and run it through a compiler which figures out what circuit to build. Very cool, but this is, for those of you, I'm going to use some jargon, NP hard problem. You can't solve this problem. You can use heuristics to come up with some solutions, but it's really funny because their debugging technique is, if it doesn't converge to a solution, change your input seed and try again. And we've done some hello world problems on FPGAs and it's taken hours to compile because it's looking for the best. It's having to route all those circuits. It's not making assembly code, it's making circuits. So potentially, the OpenCL has the advantage that we can program for it, but it's still unclear if they're going to make it actually super easy to use. We hope. All right, that's me.
So we'll take questions at the end. So Maria, go ahead and go. I'll stand here and you say forward, I'll push the next button. She's unmuted.
She's unmuted.
Oh, you're muted.
Hang on. Maria, we're going for?
All right, looks like you're unmuted now. Go ahead.
Okay. Hello, everyone. My name is Maria Vyushkova. I'm from the University of Notre Dame, and I'm going to talk about quantum computing as an emerging technology today. So quantum computing is a new and rapidly growing field, which is right now in the stage of transitioning from being researchers solving some real life problems. And this new field holds great promise to totally revolutionize the field of computation. So could you show the next slide? So quantum computation is information processing using quantum mechanical phenomena such as superposition and entanglement. And in contrast to classical computers, in quantum computing, the information is encoded in in contrast, be in a continuum of states, not just 0 or 1, so not just a binary set of states, but they can be in the state 0, state 1, or a superposition, coherent superposition of both of them, which is represented by the Bloch's sphere in the picture. And also there is one more interesting property called entanglement, and Einstein called this property spooky action at a distance. So no matter how far away from each other the two qubits are, and even if they are measured independently, they still state correlated, which is more correlation than it is even possible in any classical system. And as early as the year 1981, Richard Feynman proposed that quantum computation or computation based on these principles can be used for exact simulation of inherently quantum processes in physics and chemistry, which to classical computers. And since that time, a lot of theoretical research in the field of quantum algorithms have been conducted, and it has been shown that indeed quantum algorithms or quantum computation can provide a huge advantage over classical computers for certain set of problems. And it can make it possible to solve exponentially hard problems in contrast to classical computers. But the only problem there was the distance between theory and practical realization, and more specifically, physical. But very recently, first quantum computers finally became commercially available, so there was a breakthrough achieved in that direction, and a number of competing physical qubit realization have emerged, including the earliest one was based on trapped ions, laser-cooled trapped ions, which are two-level systems, like in IonQ machine. But the most promising one today is believed to be the superconducting architecture, which is used by IBM Q, probably the most well-known one, by D-Wave and Rigetti. And the newly emerged approach, or newly emerged architecture, is the solid-state spin-based architecture. So the situation can change at any time, because the latter technology is very, very promising. So could you show the next slide? Thank you. So there is a very common misconception that quantum computers are going to replace classical computers, or that they are going to overcome the Moore's law limit, but this is actually not true, because quantum computers and classical computers are good for different tasks. So they are in fact complementary to each other, and in that respect they are probably similar to FPGAs. In the future, I believe that hybrid quantum classical approach will be the most promising, the most beneficial. So, and as for tasks or applications where quantum computing offers significant advantage. So there are, first of all, it is modeling or simulating infinitely quantum mechanical processes in chemistry. And I'm a chemist, and that's why I got interested in this field. And it is told, it is often said that chemistry is quantum computing's killer application, because it is the most promising and the most straightforward application, and it can save researchers a lot of time in the lab. Because when we have exact simulation in, let's say, in quantum chemistry, you can speed, say, material design or drug discovery much faster and more cost efficient. Other important application is optimization problems in a huge variety of research areas, including machine learning, social science, computation, biology, even weather prediction or space debris problem, or even such problems as terror network detection. And the two most famous applications are about integer factorization and quantum search, so-called Shor's algorithms and Grover's algorithms. They were developed about probably 20 years ago. And integer factorization obviously will have huge implications for cybersecurity, for cryptography, and that's why post-quantum and post-quantum cryptography became a very important research area, and specifically post-quantum cryptography is rapidly growing research area these days. But it is believed by the experts that these two applications will be possible to implement only after many years of research, because a universal large-scale fault-tolerant quantum computer is required for that, and such computers probably won't be developed within this decade or within next decade, so it will take some 20 or 30 years before such computers will be developed. And what we have now is so-called approximate universal quantum computers, but nevertheless they already can solve real life chemistry and optimization problems. But at this point they are just small-scale toy applications. But I believe that within several years they will be able to solve some large-scale real-life problems, and that will definitely revolutionize these fields.
I think you were muted, sorry.
Oh, sorry. All right, we're on to the next technology, singularity containers. Anita, go ahead and start.
Can you hear me all now? Yes?
Yes.
Okay, perfect. So it's interesting that we talked about this as an emerging technology, and the only reason I had suggested it is because obviously containers have been around for quite some time. The concept of containers and virtualization, but in particular with singularity, why I thought that it was an interesting idea was that it was designed specifically as a solution to meet the needs of scientific and application-driven workloads, specifically on HPC. And it also, from a support point of view, it enables users to have full control over their environment to create containers that can be used for their scientific workflow, the software libraries, and even data. So I guess the idea is, oh, actually you can go to the next slide, sorry. So I didn't spend a lot of time at this point going into the details because there's a lot of documentation about, and as I said, containers and the concept of containers has been around for a while. So what I really wanted to focus on today was just to talk about the differences between singularity, what makes singularity at least attractive to our group, and why we ended up installing it on our most recent cluster. And it was interesting at PERC, there were a number of discussions around the software and trying to come up with software, better software design, and the fact that we depend so much on this software, but not very many of the people that are writing the software have experience in software development. And so what we've noticed is that our systems people spend an incredible amount of time helping people get software stacks installed or software flows installed on our cluster. In particular, I'm going to refer to TensorFlow because that seems to be one of the ones that a lot of people refer to as something they want to use. And what we've found is that it's very difficult to install in a different environment. And so in the case of Singularity, the type of, you can, I guess, move to the next slide. The nice thing about Singularity is that it's different from the other container solutions that what we liked. For example, the reproducible stack, software stacks, in the sense that you can verify them, that, you know, it's not layered. They contain everything that you need, and it's easy for you to be able to check some and sign to make sure that they're valid. The mobility of the computing, it allows them to transfer and store the actual containers that's in a standard data mobile tools like rsync and SCP, and that they can be maintained and the data controls for compliancy to meet things like HIPAA, for example. They're also compatible with complicated architectures, so they support things like GPUs. And you can get running, things that are running legacy kernels and things like that. You can be able to support those specific namespace and be able to have access to the existing file systems and structure on your cluster. And then lastly, the security model. They really hit the points home that we've worried so much about trusted users running trusted containers. And that was always the model, the security model in previous systems. And now their particular Singularity looks more at running untrusted containers in an, untrusted containers by untrusted users. So that really changes the way that we think about how people will use containers and how they can set up their software flows, but it also gives the power for the users. Now, as we always talk, with great power comes potentially great problems as well. But the benefits, if we can go to the next slide, they are easy to use, and it is a very well documented system. And there are repositories that exist. So a lot of people have contributed containers. What it allows people to do is to minimize perhaps their uptime in getting started to solve a solution. And maybe it's not their permanent solution, but maybe it's the easiest way for them to get going. It provides the HPC application portability in the sense that it not only supports MPI applications, but it can support just about any application in the pipeline, including things like GPUs and other special hardware or specific versions of the OS. So it provides that flexibility. We mentioned before, you can build this on your local system. You can do some prototyping and testing, and then you can copy that container up to a cluster and try to scale it to run different applications in that way. And especially these repositories, I should mention that they can easily use the ones that already exist for Docker as well, which is a big advantage. And the repositories provide sharing and time savings. So people, again, can take those repositories and use them to be able to get started quickly. From our point of view, I do say that the benefit is that it minimizes support. But there's a caveat to that, as with all of this. We have to have people who are at least understanding and versed in the basic technology of Singularity. We have our systems people installing it, making it available. In some cases, like on bridges, they use modules. On our system, we have a package that our systems people wrote for our environment called Ballet. And so they have to install it, make it available. And then, you still have to have people that are actually going to support it from that point of view. But because it's well documented, and at least the studies have shown, or the performances associated with using Singularity, there is minimal overhead associated with that. So again, I didn't provide all of the details about the advantages from a technical point of view by showing the great things about where it runs in the shell and how it makes it easier for users to be able to move from one system to another. But again, that's all well documented on the Singularity page. So that's all I have to say. So thank you.
Thank you.
All right, thank you, Nita. Move on to the next talk. Sean, go ahead.
Okay, let me start my video and see if this is working. All right, it is. That's freaky. So yeah, I'm just going to talk for a few minutes about the Open from Ohio Supercomputer Center, which we've been involved with for the last 12 to 18 months at Tufts, and I'm actually surprised at how excited the system, how excited I am over the system. It's really proving to be something that our users are benefiting from. So let's go to the second. So OSC On Demand is an open source NSF funded project, originally part of Ohio Supercomputer Center's web-based portal. And now they've branched it out and made it available to anyone who wants to download. There's the DOI you can connect up to find out more about the project. Fortunately, it's clientless, web-based, so there's no heavy Java or anything that you have to download. It has built-in file management capabilities. You can upload, download files, view basic things like PDFs, various images. You can edit text, C, Fortran, variety of code, access the command line through the web interface. There's a job management system that works with multiple schedulers, including PBS and Slurm. And of course, you can launch graphical applications as well as full desktops, be it if they're X11 based or web based. I'm actually really starting to prefer things that are web based. They feel more integrated than a lot of X11 applications, but it certainly does work. So let's go on to the implementation slide, if you would, please. So these are some of the questions that we were prompted with to answer during our slides. And I'll go through this. It's, I think, very practical to implement for small and large HPC centers. The latest version of on-demand is RPM-based. Yep, it uses RPMs. I think it's applicable to all research domains. We found that everyone is interested in accessing the cluster through our web interface. Even the more experienced users from physics who are maybe working with CERN and things like that seem to be enjoying it. Obviously, they're not using it to copy, tens of terabytes of data through the web interface or anything. And of course, this hits the long tail of science where you can get a lot of new users in unexpected domains online within minutes, which I think everyone can appreciate. You don't have to set up Sigwin or any kind of X11 solution. On demand is very low overhead. You simply just need to set up a small web front end, couple of cores, 4 or 5 gigs of RAM per core, and you should be able to handle dozens of users with no problem. Currently, we have it talking with Tufts LDAP server, so it uses the same credentials as our HPC clusters. There's a training manual available that I believe OSC said that you can repurpose for your own use. We have not yet gotten to that point, but I believe it is available. And like I said earlier, the feedback from all our users has been very positive. I actually, in a way, consider this to be disruptive technology because, let's just face it, all users expect a web interface to everything now, right? I think regardless of demographic or age group or whatever, we're all so used to getting things within minutes through the web that the burden of setting anything up just to get to your HPC resources has probably passed us by. So if you would go to the next slide, I'll talk briefly about the community surrounding on-demand. Obviously, there's a website. I encourage everyone to go to it.
I don't have.
Yeah.
All right, hold on a second.
No, take your time.
Okay, so the question from TV Land is there an implementation that we can test, that is to say, play with?
Yeah, so it's been about 18 months since we originally did this, so hopefully I remember all the details correctly. At that time, we set up a small virtual that was basically just a clone of our login node, and then set up the on-demand stuff through that. And OSC helped us initially, and then I went and did a version of my own. But I believe that they now have a Valgrind recipe that you could get up and running more quickly. But definitely, if you could just set up a vert that's a kind of same capabilities as your login node, it needs to be able to access Slurm, it needs to be able to access the shared file system. You should be up and running in about an hour. We really had no problems at all. I think that answered your question.
Favorite vagrant files.
Vagrant. Okay, good, yeah. Okay, should we go on? Okay, cool. So the community surrounding it, they have a website. I encourage everyone to go to that. It's really well done. And they have links to their mailing list, documentation, and GitHub. So I didn't really see the need to duplicate that there. The mailing list has been not overwhelmingly chatty in the last few months, which I think is good. It doesn't really seem like people are having a lot of problems installing this. But at the same time, of course, we'll get chattier as people start to hopefully adopt the product. We'll see how that goes. But I can say that the community provided by OSC, as well as the early participants, has really been fantastic to deal with. And that's part of my strong interest in not only participating at Tufts, but encouraging others to participate as well, and to continue to develop the really fantastic community that seems to be emerging. So if you could go on to future. Okay, good. So of course, this is all just speculation on my part. As always, the caveat is anything regarding on-demand that turns out to be fantastic and useful to people, be sure and credit the OSC group. And anything that's speculative and who knows, maybe way off base on my part, well, you can just blame me. But personally, I would like to see the future of this product as perhaps being the standard web-based interface for HPC sites, large and small, maybe even standard interface for other Exceed sites. I would like to see more community contributions. Tufts has created some modules in-house to give things like a graphical display of quota for various project spaces on our GPFS file system. And there's a little button next to your quota where you can put in a ticket to have that increased. Various other things like a web-based interface to show what groups you belong to and so on. All of which have really allowed our users to answer a lot of questions that they previously would have just sent in a ticket for. And it also allows our junior staff to answer questions on behalf of the users without necessarily having to learn the command line. Obviously, they're going to at some point, but for everyone involved, this helps get them up and running as quickly as possible. Obviously, in the current funding model for everything in the United States, is there a sustainable development model around this? Who knows? They've been renewed for a couple more years of development. I don't really know what the group plans on doing after that, but I think it's something that would be very beneficial for all involved to start discussing now, so we're not surprised by what may happen later. And I guess really what I want to say in the end is take off. This kind of seems like a singularity a couple of years ago where a lot of sites were talking about it. And then all of a sudden there was a huge uptake and now singularities everywhere. Personally, I feel and would like to see that happen with the OSC on-demand web portal. So maybe we can all work together and help make that happen. Okay, so that's enough babbling on my part.
All right, very good. So let me get this straight. That's not good. All right, just 1 second.
Am I on? Sure. Can anyone on Zoom hear me? If you can hear me, my slides are chopped off because of the phone for widescreen presentation. So I've posted a link to the actual Google Slides in the chat section.
All right, hold on a second, see if I can get them.
Thanks, Henry.
There we go.
Sorry, I'm looking off screen because I had the video on my second screen.
All right, I think that's good. All right.
Sorry, is that better? All right, I'll go ahead. So I'm going to talk a bit about Hadoop, MapReduce, Apache Spark, and big data. It's sort of ironic to call this. Can move on to the next slide. It's not really all that new. I think the first paper on the Google file system appeared in 2004, and within a couple of years, HDFS was out and so forth. All right, so this is what I'll be talking about: overview of the Hadoop Zoo, the ecosystem, bit of outline, and the challenges in running the Hadoop ecosystem, Slurm, and parallel file systems, and all that kind of stuff. Next slide, please. Sorry, I have to make sure I'm looking at the right slides. Next slide, please. Okay, so it's a large ecosystem based around HDFS, which is the distributed file system. It's really a distributed key value store with a file system-like interface over it. There's Yarn, which is the resource manager plus job scheduler, and that should ring some bells for you. You should think of it as like a Slurm or Grid Engine or Torque or something. And then the big data analysis applications over it. MapReduce is the granddaddy, and Spark is a newish implementation. And I'll talk about differences between MapReduce and Spark in a slide or two. Next slide, please. So just as an indication of how big the ecosystem is. So you start with the HDFS underlying it all, Yarn, the resource manager scheduler on top of that, MapReduce, which was the initial sort of application framework, and a bunch of this other stuff on top of it, Spark, HBase, which is like a database kind of interface, machine learning frameworks, and they're actually like graph analysis packages as well. So many of these subsystems that the Zookeeper was created to handle and manage the interactions between all these various frameworks and APIs and so forth. Next slide. So yeah, I'm no expert. My exposure to this stuff has been through a Coursera course taught by San Diego Supercomputing Center, and also a machine learning sequence on Coursera by Andrew Ng. And I also hacked a couple of versions. And as you'll see, I wasn't terribly successful. So what's in your ecosystem? I've already mentioned this, but I'll say it again. It's a distributed, scalable, portable, non-POSIX file system for the Hadoop framework. So everything in here is actually written in Java. Hadoop, HDFS, Yarn, Spark, MapReduce, they're all in Java. HDFS has shell commands and an API that make it look like a file system, but it's very important that it's not. So what's different about this than traditional parallel file systems? This takes all the local disks on each of your nodes and presents it as a single virtual, like, distributed file system. And it's a client server architecture, rather a coordinator architecture. Each node runs a daemon, and then there's a master node that coordinates who has which pieces of data, and that's how your job knows if it's close to the data it needs. There it is. So the master is a name node, and a bunch of data nodes are on the individual compute nodes. Oh, sorry, I forget I have to tell you. Next slide, you can just flip on the next 2 slides. Just quickly, there's not much you have to read. And next one, all right, yeah, and pause on the architecture. So you see the name node that coordinates where all the pieces of data go to the individual compute nodes, or what they call them, data nodes here. And it also tells the jobs where the bits of data are. Next slide, please. And here's an example on the command line. If you're sitting on a terminal with an terminal interface to your Hadoop into the cluster, so they have these Hadoop FS commands, make their put, ls, and so forth. So it looks a bit like a file system. And it looks a bit like you're doing SCPs and so forth, or remote commands. Next slide. Yarn is yet another resource negotiator. So this, because you have a big cluster of machines doing all the analysis and where all the data is split up, you need something to coordinate where the pieces, where your jobs go, so that they are on the nodes where the particular pieces of data it needs are sitting. And so this should remind you, like I said, of Slurm or Torque or Grid Engine or something. It has also a bunch of pluggable scheduler policies, which is, that's fairly common for us in HPC. The job submission, you don't write a separate job script. All that is within your program that you write that uses the MapReduce or the Spark APIs to do your analysis. Next slide. So this sort of mirrors the HDFS architecture. You have the resource manager on one master node and node managers on all the individual compute nodes. And that tells all the sub-jobs is when the jobs are done, and they send back the intermediate results and then get a new job. Next slide. So MapReduce is the sort of original application framework for Hadoop. It's sort of like because I am a bit more familiar with MPI, this is sort of like a scatter gather. You take your data, you split it up across a bunch of nodes, and you take your analysis and you run the same operations on the data that the node is on, right? So that's the map. And then the reduce is when you take all the intermediate results, gather them all, and do one final operation to reduce it to your final result. Next slide, please. And here's an example. I've elided all the actual stuff in the mapper and the reducer. If you go to the next slide, your main method in your MapReduce program, that's where you see you have all your job submission stuff. This is just to illustrate that this is really like what we think of as HPC cluster. And the next slide, please. To run, yeah, you just submit the job and that's it. Now, next slide. So because Hadoop thinks it has the entire cluster of hardware for itself, how would you fit it in a typical HPC cluster? And the answer is kludge or hack, and depending on your point of view. Next slide. Right, so this is just what I said before. HDFS handles distributed storage, Yarn handles the distribution of tasks, and MapReduce is your jobs to be distributed to the cluster. Next slide, please. So what if you have already a parallel file system, Lustre, GPFS, whatever? What you can do is, or what some of the parallel file system vendors have done is replace the HDFS APIs with, oh, you cannot see my face here, replace the HDFS APIs with plugins to the underlying parallel file system. So to your MapReduce application, it doesn't look too much different, except now it's calling a layer that's an HDFS compatible layer that interfaces to the underlying parallel file system. There's stuff for Lustre, there's stuff for Ceph, there's stuff for GPFS. And next slide. Yeah, so that's it. And how about the resource management and job scheduling? Because, sorry, I'm glancing over at the chat to make sure I'm not missing any questions. Okay, wouldn't the Yarn scheduler conflict with the, your Torque or Slurm or Grid Engine? The answer is yes. So that forms the basis of the hack, really, to get Hadoop to run in an HPC cluster. And a bunch of vendors have also provided their own interfaces. Grid Engine has Hadoop integration for Cloudera distribution for Hadoop, which is a nice sort of pre-made commercial package that gives you the entire ecosystem in one easy to install image. Oh, sorry, did I skip over? Yeah, so the solution for running Hadoop on an HPC cluster is, so you submit a cluster job, which gets assigned a bunch of nodes. You take the nodes that are assigned to that job and you set that up as an ad hoc Hadoop cluster. So within that, Slurm job or whatever, you start running all your Hadoop services. So you have a mini Hadoop cluster running inside your HPC cluster. So that's really how things are done. Resource management, sorry. I'm sorry, next slide, please. Yeah, good. Yeah, so Slurm also has an interface. Lawrence Livermore has this thing called Magpie. It's a bunch of bash scripts to run the Hadoop Zoo in HPC. It supports a lot of stuff. Hadoop, Spark, HBase, Storm, Figma, Hood, blah, blah, blah. The schedulers it supports are Slurm, Moab, Talk, LSF. It also supports as parallel file system, Lustre, and other shared file systems. There is a much older version produced by Harvard. It's called just HPC Hadoop MapReduce. It's one big bash script, works for Slurm and LSF. It is old, it's written 2013 was the last check-in I saw on Git. Next slide. SFS Lustre user group meeting in 2013. So Intel presented some stuff where you can run Hadoop on a Slurm environment. I think it's proprietary. And they also talk about Lustre replacing HDFS. All right. And we can go to the next slide. Apache Spark, and skip to the next slide. So what's Spark? Spark is sort of a replacement for MapReduce that tries to improve performance. So the difference between MapReduce and Spark is that Hadoop does all your operations, reading and writing to the node local disk, whereas Spark tries to do it all in memory, meaning it just does one big read in memory, does all the computations that it can in memory, and it only writes stuff out when it absolutely needs to. So all intermediate steps are all done in memory. And that's actually proven to be pretty fast. And the other useful thing for HPC people is that it does not require HDFS and does not require yarn, which is how I managed to come up with my kludge. And it's there if you want to look at it. It doesn't work completely well. Sorry, next slide. And without HDFS, next slide. So you write, this is for Grid Engine, you can write a PE script, which is a parallel environment script for pre-launch that sets up all the environment variables that Spark will read in order to form its cluster. And next slide. So that's it. So there are multiple solutions for using the Hadoop frameworks in HPC. There's a support for various resource managers, schedulers, and various file systems. It's a bit kludgy, and the stuff may not support the latest Hadoop. That's it for me. Thank you.
Thank you, David. We're going to open up questions before I throw out my questions. Throw out questions to the floor. Does anybody have any questions for any of the presenters? All right, hold on while I get to my questions. Because I'll just hold down the key and I'll eventually get there. What's that? All right. So there's questions to the panel then. So I guess the question is how practical would be to implement the technology you talked about with a staff of HPC center or CI center with a staff of 5 to 10 people. You want to go first?
With the FPGAs, it's pretty easy. I mean, the tools and stuff are available for purchase. However, actually getting something out of an FPGA right now, there aren't any killer apps driving it. So unless you have an application area that already has something implemented in FPGA, I don't think the investment's worthwhile. I mean, the reason we're investing in it is because we have people developing large-scale algorithms that we want to port to the FPGA. That's their research. And so that makes sense, but most people aren't doing that level of research. And so until these applications start supporting FPGAs like, you know, or machine learning or whatever, genomics, I think you've got to wait for the killer app before you bother purchasing them.
So would you say like some of the ASICs when it comes to the tensor cores or tensor?
You would have to, it'd be driven. You can't do much with an ASIC, except what it's designed to do.
Do you know what the difference between the tensor TPUs and the tensor cores inside the GPUs are?
They're faster. So the ASICs are always faster.
Always faster.
Well, always. And then the next generation of GPUs come out and they beat them. But you usually can get the hardware going. Yeah, you had a comment, Rob?
Do you have experience installing ASICs in an HPC environment?
I've never justified it. So installing an ASIC in an HPC environment requires very specific workflows. I've always worked in a general purpose HPC environment where we're there to support all researchers. When you have an ASIC, you are doing one type of math. I'm not saying it's impossible, but I don't see it. I mean, FPGAs are at least flexible in that you can make them do multiple things. And where we get really excited about them is, can we put 2 types of chips on one FPGA so that workflows, different bottlenecks in your calculations can happen in different places on the FPGA. there could be some potential really interesting things you could do, like taking the advantage of GPUs at the same time taking advantage of like a TPU or something.
Maria, how about a quantum computer? My guess is not too much future for small centers in the near future.
No, that's actually not true. And I think for a small center, the most practical solution will be to get a cloud access to a quantum computer. For instance, IBM Q has made the small 5-qubit device available to the general public in a cloud, and also can get access to 16 qubit and 20 qubit. You just need to write an application. And also Rigetti has made their quantum device need to contact them to get access. And also there is so-called quantum computing testbed project at Oak Ridge National Lab. So they provide access for researchers to both IBM Q and IonQ machines. So actually, yes, it is possible, and it is very practical. You don't really need to, let's say, purchase a quantum computer, right? You just can get access through a cloud. And also, I believe that it is, at this point, it is just not practical to purchase a quantum computing device, just because at this point, at this moment, there are a few competing physical qubit architectures, and it is yet not clear which one of them will be more successful in the future, or some new technology will emerge. So the most practical approach is to get a cloud access, which is very easy to do.
So you said you could apply to IBM for access, or Oak Ridge, or what was the other one you said?
Rigetti. Rigetti, that's Rigetti, yes. Quantum, yeah. It's a smaller company based in California, so, and they focus on developing quantum software and developing the application ecosystem. But yes, they also use a superconducting qubit architecture, and basically just need to contact them, basically just send an email to them and request access to the machine, and just schedule your time there. Which is very easy.
Very good. Anita, how about Singularity?
I think that's very doable. And as we've talked about, or as I mentioned before, you know, the concept of containers are not really an emerging technology. It's just the idea of using containers in an HPC environment is more of an emerging technology in a small HPC group or center.
Sean, how about that on demand?
Oh yeah, I definitely think it should be no problem for anyone to implement. It probably only took us 20 hours to do, and that was really, we're going to redo our instance soon and put it behind an enterprise level load balancer and treat it just like any other enterprise instance. And of course, that's going to take a little bit more time, but the enterprise team already has that set up for other stuff. So I don't think that will, you know, be anything unexpected. I definitely encourage everyone to at least look at it and see what they think.
Any questions? David, how about Hadoop? It looks like Hadoop had several different routes to use, but it also looked kind of complex.
Yeah, if you just want to do Spark, and that's fairly easy. It took me a day or two at most, because you can just avoid HDFS and Yarn. yarn. So that's pretty easy. And then with the LLL Magpie scripts to integrate with existing, scheduler plus parallel file system, it's pretty straightforward. I have not, however, installed HDFS itself, nor yarn. I imagine that would be fairly complex. All the other stuff on that big zoo diagram, I have not even touched, so I don't know what it would be like to try to install all of the entire ecosystem.
Okay. So, so which domains do you feel like the technology is most useful for?
I'm not sure yet. We're going to see it in of bottlenecks, where you need to maybe take advantage of GPUs in one part of your bottleneck, but maybe you need something else in a different part of your bottleneck, and being able to switch between optimized workflows could potentially be very interesting. Again, we are really just kicking the tires. I'm not sure where it's going to really succeed and really fail. I think we're kind of like in the early stages of GPUs. We got to try some things and see how it goes.
What do the folks? I mean, I've seen a couple of times at Super Creative with FPGA vendors. What do they say?
Well, okay, the vendors I know have been selling a lot of assembly and GPU genomics related boxes specifically designed for that. I haven't touched that yet, so I don't really know what's available. There's a hand raise, yes.
So yeah, there's a company called Encode Genomics. It's a limited company that makes sequencers for gene sequencing.
Louder and slower.
Encode Genomics is a company, it's an Illumina company. Illumina is the people who make the gene sequencers. They have an FPGA-based system called Dragon, which stands for Dynamic Read Analysis for Genomics. And so the hospital, the Kansas City Children's University Hospital, had a paper that came to having supercomputing conference a few years ago, presented how they went from just having a normal cluster using this Dragon FPGA to reduce their genomic sequencing analysis time from like 40 hours to like 2 or something. Just a scale reduction of the time. And University of Minnesota talked about that at Berkeley 2 weeks ago, how they're using the Dragon processor in the cloud right now to test some of the workflows for their bioinformatics. So my question to you is, do they own some sort of intellectual property on a bioinformatics VHDL for the FPGA, or is that stuff open source? You can call any of it?
I don't know the space yet well enough to know if there's some open source solutions. I do know some companies have closed source solutions, that's what they're getting their money out of. Again, it's been around for easily 20 years. I taught it quite a few years ago, but in the HPC market, there's been a few cases of breakthroughs. If you have a very homogeneous workflow where you're just doing the exact same calculations over and over and over again, people build these computers that go in and do that calculation for you really nice and fast. They might even do an ASIC in those cases. What we're excited about is the reprogrammability of these things and looking at what we can do to speed up algorithms in ways that GPUs and CPUs can't. And I think that's where the hope is to head towards something like an exascale system, where we maybe do a pairwise all comparison in one clock cycle, or similar things to that. I'm sorry if I use jargon, but like a really complex algorithm, maybe they can do it really fast and just implement that, and it's a function call from your code. That would be really cool. But I'm just still new at this, and so I'm not sure what you can and can't do. There's a lot of things. I know MPEG encoding, super efficient on FPGAs. So if you have a lot of video you want to encode with MPEG, FPGAs are the way to go. But that's one particular weird algorithm.
So Maria, you talked about a number of applications in your talk, but I don't know if there's anything more you want to add where you see it maybe going that maybe you didn't mention before?
So the most the most important applications are obviously physics and chemistry, and more specifically quantum chemistry simulations and spin chemistry, and in physics it's solid state physics and nuclear physics, particle physics, and also a very important applications which is talked about a lot is machine learning. And there are also many interesting new applications in social science. So basically, quantum computers are good at performing optimization tasks, and that could be relevant to different research areas. And the IBM Think conference this year, they talked about solving the space debris problem, the orbital debris problem, using quantum computers. So, and they propose that they can use quantum algorithms for solving the travel and salesman problem and just detect the orbital objects which are dangerously close to each other before something bad happens. And they are working on developing quantum algorithms for that. Or I think Los Alamos National Lab was working on a project which involved using the D-wave quantum annealer for detecting the terrorist networks. So it is for social network analysis. And recently, as far as I can remember, that was the UK government. They invested a significant amount of money into development of quantum computing algorithms or approaches for weather prediction. So there are a lot of different applications in very different research domains. But at this time, probably the most promising are physics and chemistry and machine learning.
I'm going to change the question for you a little bit. So how can singularity be used for results reproduction or reproducibility of scientific results?
Okay, so can you hear me okay now? Okay, so I think the idea is that, you know, with respect to research domains, this allows people to really set up and work with those scientific applications and workflows, the pipeline, and actually target those specific domains and help them to be able to accomplish their work. Make it easy level and getting in. People do a lot of experimentation on their own local systems. And I think that for them to be able to see how clusters, this is one way for them to have that easy entry and that comfortable environment to be able to get started. And then later actually looking at those specifics of what they might want to do to make it more native to the cluster, or how they might be able to increase their performance if that's necessary, or even maybe change their workflow. But this allows them to be able to easily use an HPC environment.
Very good. Any questions? So David, I've never been entirely clear what Hadoop or Spark would be used for. What sort of applications and domain spaces are that technology applicable to?
So the most obvious one would be, say, if you have a linguist or maybe a computer scientist who is interested in subscribing to the Twitter firehose with a big Internet 2 connection, you could do that and do your streaming data analysis on, you know, the firehose Twitter feed. Or if you manage to download a large corpus of data, whatever data that might be, run analysis on that. here we have one researcher who's doing machine learning applied to bioinformatics. So if their data set is large enough, there are machine learning packages for Spark. So you could run ML on these large genetic data sets. Those are the off the top of my head.
Yeah, good.
Yeah, I just want to add one more. I was sitting here thinking about it. One of the neat things about FPGAs that has the potential is that GPUs are sped up by doing this, lots of little cores doing the same thing at the same time. And so to code them, it gets kind of tricky because you have to make them all do. If they branch or if one thread does something different than the others, it can slow down a GPU. One advantage, a hope of FPGAs is that they might be able to find speed ups that don't have to do exactly the same thing at the same time. You do many things in parallel, but they might be completely different things, just how they're wired. So that could be potentially really interesting.
I think we already talked a good bit about how people can get access to the technology. Let's skip ahead here. How easily can the training materials be accessed for different? So, you talked about you had. Is there any training materials you don't actually have to have a PGA to start looking into?
Actually, that's a good point. FPGAs, the Intel compiler has a simulator mode that goes. I forget what it's called. There's a name for it. Someone can look it up. But there's a simulator mode. Actually, you do most of your development in the simulator mode because it takes so long to compile. If it can take 2 hours to compile, you're not going to be debugging on actual hardware. You debug in their simulator mode. And I'm pretty sure you can download at least an evaluation version from Intel for the OpenCL simulator mode. That potentially could be a great way to get started and just to see if you think it will run faster. However, the simulator mode, in our experience so far, is just an estimate to run it on the hardware to actually see what happens. So that's.
But it could be a good way of justifying maybe possibly getting the money to buy one.
Yeah, and Intel has a lot of for-pay tutorials, but they also have a huge thing of videos and stuff you can download and just watch that are free, especially to academics. And so my student was able to get things running pretty darn quickly, having no experience in FPGAs prior to that.
About quantum computing, is there materials out there that you can sort of get a head start before you maybe reach out to IBM or some of the other companies?
Yes, yes, that's actually also very it is also very easy to do. So there are a very good free tutorials available online from IBM Q and Rigetti as well. So, and there are a lot of educational videos by IBM available on YouTube. So, and these are really good training materials. And this is actually how I personally learned to use IBM Q and write my first quantum circuits. So those tutorials are really good, and there is also a huge quantum computing community. So IBM has put a lot of effort in developing such communities. So you can talk to people, you can connect to them, and you can discuss the problems you are facing. So yes, you can very easily get access to very good free training materials.
Very good. Anita, what would you say the best training materials are for Singularity?
Well, definitely the documentation that they have available on Singularity's site is, I think it's excellently written. It provides a lot of examples, and they also have tutorials as well. So, and even going to conferences and things like that, they offer a lot of tutorial courses just, for, I guess, a half a day or a day. And that's certainly sufficient, but I think that most people who have used this type of technology before should easily be able to follow along based on what they already have up on the sites.
Very good. And then Sean, how about on demand? How obviously there's lots of stuff to download. To be trained up and getting it installed.
Oh, getting it installed. Well, from that perspective, the website has pretty much everything you need. It's some of the clearest documentation I've ever read to getting stuff installed. So just go to the website and find the installation link, and honestly, you should be ready to go pretty quickly. Some work needs to be done, I think, on the user-facing stuff. At Tufts, we've borrowed their user manual and repurposed it for Wednesday training meetings that we invite all our new users to. Does that answer your question?
Yeah, I think so. So you're in the process of refining the user side of the documentation?
Yeah. You know, we generally rebrand things, and OSC has said that you can pretty much, you know, with proper attribution, do whatever you want with the manual that they do have available. Of course, I worry, having said that publicly, that they're going to come back and say, no, Sean, that isn't what we said. But it is available. And I think if we could all maybe, who knows, maybe we could all start working on that together. There's some stuff in the HPC community on Slack and things like that, and Exceed that is trying to get some overall HPC manuals that sites can, you know, repurpose. So maybe this could all work together.
Very good. David, how about Spark and Hadoop? What kind of training materials are there available? What would you recommend?
So the both Spark and Hadoop, there's plenty of good documentation. Spark, I'm more familiar with Spark than Hadoop and MapReduce. It comes with a whole bunch of example applications that show you, starting from a simple thing, which is the word count, say, and going to more complex examples. Because big data analytics is huge now, you know, every business wants to run it. There's plenty of material on Stack Overflow, all the usual question sites, blog posts, blah, blah. And if you want formal and non-free stuff, Coursera offers a bunch of courses, a couple of which I've taken. Like one of them was from the San Diego Supercomputer Center. So they do, yeah, they touch on a fair bit of the Hadoop ecosystem. So I do recommend that. It's a 6-course series. Yeah, that's it.
How do you recommend the Coursera? I guess we can't talk about what we recommend. Forgot. One last question, since we're sort of running out of time, and we'll just go with the disruption question. What's the technology's potential for disrupting everything you do?
Hope is that it can derail the current winner, which is the GPUs, in the accelerator category, and take us to exascale. That's the hope.
So you potentially manufacturers FPGAs see them eclipsing.
That's the hope.
GPUs possibly someday.
Right. So it's a fight to see who wins. Actually, they both might win at some level too.
Right. Maria, how about quantum computers? Obviously, it's not going to happen for a while where there's widespread access. But what's the potential for disruption? How are things going to change in 10 to 20 years?
So actually, quantum computing this year was named by IBM among the 5 technologies to change the world tomorrow. So they published this list of 5 disruptive technologies every year, and quantum computing was included this year in that list of 5 revolutionary technologies. And actually, all experts agree on that this is a potentially disruptive technology, but what they disagree on is when within some foreseeable future? Is it within next several years or several decades? Because let's say the integer factorization problem, the experts don't believe that it will be solved within next 10 or 15 years. So obviously it will have huge consequences for cybersecurity, but apparently that's going to happen in the far future, because large-scale fault-tolerant quantum computers should be developed for that purpose. And at this time, the biggest problem is not the number of qubits, but their quality, so-called quantum volume. So their error rate, their noise level, the crosstalk problems. So, and this is basically the hardware problem, and it is not clear which qubit architecture will be the most successful. People are still working on that. So definitely, yes, it's potentially disruptive. Not clear yet when it will be attainable. So.
Very good. Anita, how about change things, or how should it change things?
Well, I certainly hope that if people, more and more people moving to singularity is just, as I said, it's just going to increase the entry level of people being able to do their work. So I think as a container, the idea, plus I'm hoping that the repositories will grow and there'll be more sharing, and people will have worked through a lot of problems by using this and being able to pass that on.
Very good. Sean, I heard you say disruptive earlier.
Sure. Yeah. I mean, it's a web portal to HPC is going to be disruptive, like quantum computing or anything like that. So I will actually say it's more, I personally think at this point, expected technology. So somewhere between expected and disruptive, simply because everyone expects a web interface to whatever they want in the world. And I think there's some gateway research from the Exceed sites that show what 60–70% of the traffic is now coming through gateways, and this will just be a continuation of that for all the other sites.
How about Hadoop and Spark technology?
Sorry. I think it's a pretty good potential. San Diego has this application where they take streaming data from environmental sensors around the state, so to monitor wildfires, which is kind of a big deal right now. And they run it through their big data analytics engine at the supercomputing center, and help their firefighters and know where the fire might move to. So that I think as soon as researchers start to pick up more on the big data tools, than what I can think of right now. So yeah, I think that's a very good potential.
Do you think a lot more real world applications might come about? Okay. All right. Well, we're getting close to 3 o'clock here, and I know a lot of people have to leave here at 3. So let's thank our panel.